Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 12 students studying advanced functions in the trigonometry part of the course. In this video we'll be looking at making sketches of the reciprocal functions and also tan, and then how to apply transformations to those sketches. So just a reminder from either the last video or obviously from class that this is what those four functions look like. You've got here's tan x with its asymptotes, and then the reciprocal functions cosecant, secant, and cotangent. So these graphs need to be stuck in your brain, or you can develop them every time, just as we developed them in the last video or in class. And if, again, you don't like developing them, then just somehow get this stuck in your brain. Let's jump right into it. So here's a tan function that has been transformed, and we're going to try to draw the sketch of this. So the first thing before I do anything else is I want to factor out that k value so that I know exactly what my phase shift actually is. So there it is, it's pi over 2 to the left. So this is the actual function now that it's been fully factored. And I can see my horizontal changes. I've got a k value and a phase shift, and then I've got some vertical stretching and vertical translation. So now I'm going to try to draw the sketch of tan. So I'm going to use my kind of memory. So if you've got it memorized, that's great. Here's what I kind of think about when I look at this. I know that tan is equal to sine divided by cosine. So wherever cosine would normally have a 0 value, this graph is going to have an asymptote. So cosine is normally 1, 0, -1. So there's an asymptote here and an asymptote here. And again, that's because I know that the cosine graph is normally 0 in those locations, and tan has cosine in the denominator. And then from there, the rest of the graph is actually pretty easy for my memory to figure out, because I know that tan is a positive graph, meaning that goes from down to up, and it looks like that between the asymptotes. And then this is kind of half of a curve, and this is kind of the other half of a different curve. So that's really, again, a really rough sketch of what tan looks like. But if I wanted it to be any more beautiful than that, then I wouldn't try to do it by hand. I would ask a computer to graph it for me. So let's look at the easy stuff first, the verticals. This center line, which in an untransformed graph is at 0, is now at -5. Now in terms of maximum and minimum, normally we would take the amplitude of 3 and we would move up by 3 units and down by 3 units, but tan actually goes up to infinity and down to -infinity. So these values of -2 and -8 are actually meaningless. So a vertical stretch in tan doesn't really do anything. So if I'm asking you to sketch one of these, if you wrote -2 and -8, that's fine, but it's not necessary at all, so I'm going to leave it off, because really this is positive infinity eventually and negative infinity, so we're just going to leave it like this. Now let's look at the horizontal situation. So there's my k value, it's 2, and even though the period of tan is actually pi, we're going to use 2 pi to calculate the period of my graph. So it's a little bit of a, hopefully that makes sense to you situation, but don't worry about it if it doesn't, because what I'm trying to do is figure out what happens to this sketch, and this sketch is over a distance of 2 pi. So the transformation, the k value is 2, so the actual sketch will be between 0 and pi units. So if this wasn't phase shifted at all, I would start at 0, and this would be, oops, pi units, not 2 pi, pi. Let me fix that. But it has been phase shifted, therefore those aren't the values I want. So what we need to do now is we need to figure out, first of all, let's figure out the quarter period value, which is to take the period and divide by 4, so pi by 4. Now I know that each of these steps on this sketch is exactly pi over 4 units away. So now again, if I had no phase shift, I would know that this was 0, and this was pi over 4, and this was 2 pi over 4, and so on. But we have a phase shift, so hold on, let's deal with that. So now we need to look at the phase shift, because the phase shift tells us where this starts. The phase shift is to the left by pi over 2. So I know that the first point, or the first part of this sketch, would be at pi over 2. Now there's 4 more points to find, and I know that each of those points is exactly a quarter period value away. So I'm going to do this the easiest way I know how, which is I'm actually going to rewrite this for a minute as the same denominator as my quarter period value. So this is actually going to be 2 pi over 4 instead of pi over 2. Same thing, but now if I know my graph starts at negative pi over 4, oops, it doesn't. I know that my graph starts at negative 2 pi over 4, that's better. So the first part of my graph is negative 2 pi over 4. I've already labeled it. And then the next important point is add pi over 4. So I'm just going to add pi over 4, and that gives me where my next point will be. And in case you're wondering, the reason why, oops, oh, my computer's not happy with me at the moment. The reason why I'm doing the math here and then transferring it to the left is just in case I have to reduce a fraction. So anyway, we started at negative 2 pi over 4. We added pi over 4. Add pi over 4 again, that's 0. Add pi over 4 again, that's pi over 4. Add pi over 4 again, that would be 2 pi over 4, which reduces to pi over 2. So now I know all the important locations of all of the 5 key points on my sketch. I've applied all the transformations I need to. So this is what I would be looking for if I asked you to sketch this, because that way you could, if you had to, translate this kind of nicely into a graph. But that's not what we're worried about. We're just worried about the sketch. Now the other thing I want you to be able to do with a sketch like this is to be able to tell me the domain and range. So let's think about that. Well, the range is easy. The range for both tan and cotan is all real numbers, because if you look at just the blue line, it's going to go all the way to infinity and all the way down to negative infinity, and there's no gaps, or there's no y values, there's no vertical values that are skipped. So the range is just all y values such that y is a real number. But let's talk about domain. When we talk about domain, we have to consider the fact that there's asymptotes. So when we talk about what x is allowed to be, x is allowed to be anything between the asymptotes, but not the actual asymptotes. So I have to explain in my domain that x can't be certain things. For example, x can't be pi over 4. It also can't be negative pi over 4, but I like to take my first asymptote that's positive. No reason, it's just it looks nicer in the domain. So x can't be pi over 4. Now, I'm obviously not going to be able to list every possible asymptote location because there's an infinite number of them. So instead, I'm going to figure out what the distance is between each asymptote. So this is 2 quarter period values, or exactly pi over 2 away. So what that means is that if I start here at pi over 4 and I move to the left or right by exactly pi over 2 units, I'm going to always run into asymptotes. So asymptote, asymptote, asymptote. And actually, let me just flip over to a different sketch. Oops. Here we go. If you look at this sketch, for example, this is the sketch of, is it the same function? It is the same function. Yay. Here you can see a computer graphed it, and they've got a lot more of the graph going on. But you can see that there'd be asymptotes in a lot of different places. And those asymptotes are always the same distance apart. So if we start here at the first asymptote, let me see if I can draw on top of this. No. If we start here at the first asymptote, so just sort of follow along if you can see my mouse. If I move forward by pi over 2 units, here's the next asymptote. Or if I were to move backwards by 3 pi over 2 units, there's another asymptote. If I move backwards by 6 pi over 2 units, I found an asymptote. So what we write in our domain is that x can't be pi over 4 because that's the first asymptote. And after that, if you go forward or backwards by pi over 2 in whole units, you'll find an asymptote. So what we do is we say that k has to be any integer. If you pick any integer for k, then what you're going to do is you're going to multiply it by pi over 2, and you move forwards or backwards by that many asymptotes. So x can't be this asymptote or any value within this many asymptote distances away. So k is an element of I, and I'm running out of room here. So down here, I have to say that x is a real number. So x is allowed to be anything except for this asymptote and any value that's exactly a full asymptote away. Whew. All right, so let's talk about cosecant. What do we know about cosecant? It's already factored. We know that cosecant, what do we know about cosecant? Cosecant is the inverse of sine. So wherever sine would have a 0 value, I now have an asymptote. And it sort of looks like someone took sine and turned it inside out. So it looks like this and like this. And again, just a sketch. So let's talk about the horizontal numbers. They're usually pretty nice. The middle is at -6. And then the amplitude tells me how to get to this bottom marker, because the upper marker here would be infinity, and that's not interesting. But this bottom marker would be exactly 4 units away from that center line, and this sort of upper marker, if you want, would be 4 units in the other direction. So this sort of imaginary line here and this imaginary line here, one's at -2 and one's at -10. Horizontally, let's look at what's happening with the period and the phase shift. So the period is 2 pi divided by k, so that's pi. So the quarter period value, okay, my pen is really not happy right now. The quarter period value is pi over 4. And the phase shift is left by pi over 3. So our life is going to be a lot easier during this question if we write both the quarter period value and the phase shift in the same unit. So we're going to write them as denominator 12. So the quarter period value will be 3 pi over 12, and the phase shift will be 4 pi over 12. So I know that the first of these 5 interesting points, so let me sort of represent them here with 5 dots, is to the left by pi over 3, but I'm going to write to the left by 4 pi over 12. And then the next point is a quarter period away. So the next point is 3 pi over 12. So if I add 3 pi over 12, I'm at -pi over 12. The next one is 3 pi over 12 away. So add 3 pi over 12, -1 plus 3. That's 2 pi over 12. Add another 3 pi over 12. And add another 3 pi over 12. So those are my values in unreduced form. That's why I put them over here, so that when I go to my sketch, I can actually put reduced values. So this is at -pi over 3. This is at -pi over 12. I don't need to reduce. This is at 2 pi over 12, which is pi over 6. This is at 5 pi over 12, doesn't reduce. And this is at 8 pi over 12, or 2 pi over 3. So those are the significant values for this sketch. And again, you know you've probably done things right. If you can see like this denominator reducing pattern, 3, 12, 6, 12, 3, it actually works out nicely. So let's go ahead and talk about the domain and range of this. I feel bad about erasing, but you can always pull the video back. Haha, technology. So let's talk about domain. And I'm going to try to give myself a little more room. Domain is x, and again, because of this, x is going to be any real number except for where the asymptotes are. So we're going to say x can't be where the asymptotes are. And where are they? Well, let's find the first positive asymptote. That's pi over 6. So it definitely can't be pi over 6. And then what is the distance between each asymptote? Well, that would be double the quarter period value, or half the period, or I could just do this math. Of course, if I hadn't erased my stuff over here, I could see it more easily. But remember, the period was pi, so this is a distance of pi over 2. So every pi over 2 units you're going to find an asymptote. So we say this. So if you start at this asymptote, pi over 6, x can't be that. And also, if you move forwards or backwards by units of pi over 2, so go forward by 1, go backwards by 6, that's also an asymptote, and that's also bad. So to finish this logical train of thought, we say that k has to be an integer, so that's supposed to be like an I, right? Sort of looks like weird, but whatever. K has to be an integer, and x a real number. And that's my domain. Now my range is a little interesting here, because I have this -10 and below is allowed. So y can be less than or equal to -10, or above -2. So y can be greater than or equal to -2. And otherwise, as long as you're following those rules, y can be any real number. So there's domain and range. Whew. Next one, let's look at a cotan graph. We'll try to do this one quickly. These videos turn out to be longer than I think. So let's try to do this one reasonably quickly. Hey, you know what's a good idea? Why don't you press pause, try to do it yourself, and then come back and see if it fits. You know, just teaching ideas. So I'm going to factor out that 3. So remember, when you're factoring out a 3, it's like sort of you're doing a little division, because the opposite is to do multiplication. So this actually becomes pi over 6. Boom. And it's a cotangent graph, so I know that a cotangent graph has asymptotes where sine is 0, so that's at these locations. And cotangent is a negative graph, at least that's what my brain tells me, because it goes from a high to a low within those ooh, that's not gonna work. Let's do this. Okay. If I wanted to be perfect, again, I would ask a computer. And what values can we put on this? Well, we know that the midline is at 10. And because it's cotangent, just like tangent, even though I could write that this goes up to 13 and down to 7, there's no reason to really write that down, because it's actually positive infinity and negative infinity, and values of 13 and 7 are sort of irrelevant to this graph. So we'll just put 10 there. So now let's look at the period. The period is 2 pi divided by 3, because that's my k value. And so the quarter period value is 2 pi divided by 3 divided by 4. 3 times 4 is 12. So the quarter period value is actually 2 pi. I don't know what's happening with the video, because my computer's kind of getting weird. So hopefully this is working out. So my quarter period value is actually pi over 6. And my phase shift, oh, I like it when things work out. My phase shift is to the right by pi over 6. So they already agree. That's kind of nice. So my first interesting point is at my phase shift, to the right by pi over 6. And then I just have to add the quarter period value. So this would be 2 pi over 6, reduces. 3 pi over 6, that reduces. So 1, 2, 4 pi over 6, that reduces. 4 pi over 6. And then 5 pi over 6, that doesn't reduce. Okay, and again, you can see the pattern in my reduced denominators. That's nice when that works out. And for domain, what would we say? Well, the first asymptote, which is our first restriction, is at pi over 6. And after that, there are asymptotes every half period away. So we can just say every 2 pi over 6 or every pi over 3. Oops, I didn't mean to put a comma there, because I'm not done. Then our first asymptote's at pi over 6, and after that, they're every pi over 3 away. So if k is an integer, which is what we're saying, then you can find another asymptote by starting at pi over 6 and moving a whole value of pi over 3 to the left or right. And so k is an integer, x is a real number. And my range for cotangent, just like for tangent, all real numbers, because negative infinity, positive infinity, and every value in between will eventually be traced by this shape. Okay, I hope that has been helpful for you. You know, these are just sketches. They're not beautiful graphs. Again, if I wanted a beautiful graph, I would just say, hey, computer, make it for me. But we need to be able to understand the shape of the graph and the general transformations effect without having to rely on technology or spend too much time making it perfect. Okay, so there you go. Good luck in your studies.